Hi everyone, welcome back to the Flight Engineer YouTube channel, a channel about aviation, technology, and history. I'm your host John, a mechanical engineer with a minor in aerospace engineering, a private pilot, and an enthusiast for all things that burn gas or go fast. Before we get started here, I just need to say that this video is heavily reliant on the content from the previous video. If you haven't seen that, I really recommend you watching it first unless you have a super solid understanding of the Otto cycle and basic ideal cycle analysis. If you really don't want to do that, however, here's the quick and dirty to get you up to speed. We've been talking about ideal engine analysis, what it is, why to use it, and what limitations come with it. We're building a tool in Python that you can use to perform these analyses yourself and estimate engine performance. Ultimately, the end goal is to improve the program to the point where it can provide useful insight about real engines by taking measurements and operating parameters and generating understandable performance predictions. So far, we've talked about the Otto cycle, or the constant volume cycle, finding pressure, temperature, and volume of the working fluid throughout 4 critical process points. We've talked about how heat and work move in and out of the system, and we've produced some very odd-looking performance estimates. Now, we'll build on that base and continue to refine the simulation's predictive power. Before diving back in, I'll just give you one more bump to check out the previous video if you haven't yet. It should be linked or on the screen now. Moving on from the Otto or constant volume cycle, we'll go to the diesel or constant pressure cycle. As the name implies, it's more suited to diesel-powered, or more accurately, compression ignition engines. It's going to look very similar to the constant volume cycle, just with some changes to the combustion event and power stroke. We'll go through the process for the diesel cycle once again by looking at the engine diagram on the right and the PV diagram on the left. From 1 to 2, we have the compression stroke, which will be treated as isentropic compression once again. This section is identical to that in the constant volume cycle. The main difference from this cycle comes from 2 to 3, during the combustion event. Last time, we modeled the combustion as heat being added to the system at constant volume. In this case, we'll model the perfect heat addition over a constant pressure while letting the volume change. This is where the constant volume and constant pressure names of the cycle come from. So why do this? Well, in a spark ignition, typically gasoline-fueled engine, the whole fuel-air charge is ignited and burned at once. In reality, this doesn't happen instantly, but it's quick enough that we can simplify it to an instantaneous process. In a compression ignition, typically diesel-fueled engine, however, fuel is injected continuously over a short period of time, where it burns on contact with hot air. Simplifying this more drawn-out combustion process, we assume that fuel is being added and burnt at the beginning of the power stroke, such that cylinder pressure is maintained at a constant state even as the piston moves down. The assumption is not completely accurate to the way that real compression engines work, but the model is much closer to the real thing than the constant volume heat addition would be. After this unique combustion event, the working fluid once again expands from 3 to 4, doing work on the surroundings. Finally, the blowdown process remains unchanged from the way that it worked in the previous constant volume cycle. Let's get into the problem setup. Here, the initial conditions will be very similar to what we used for the Otto cycle. We will change compression ratio by adjusting our clearance volume, since diesel engines typically have a much higher compression ratio than gasoline ones. In this case, we'll go for an 18:1 compression ratio as opposed to the previous 11:1. Additionally, assuming our diesel engine is burning diesel fuel, we will have to change the air-fuel ratio and lower heating value for the fuel for the values of a diesel-air mixture. Other than that, all of our defined variables can remain the same. Beginning the process, we will skip the first step, isentropic compression, as it is identical to the process that was described in the constant volume cycle. Instead, we'll jump right to the constant pressure heat addition. This is going to start very similarly to the combustion event during the CV cycle, and we'll use many of the same equations, just with a twist near the end. As before, we need to know the mass of the fuel, we still need to calculate the heat its combustion will add to the system, and find the temperature rise. Before, we calculated a new pressure with volume remaining constant, but now we're going to calculate a new volume with pressure remaining constant. It's a simple but very significant change. Also, since our volume is changing this time, some work is actually done during the heat addition, and this must be accounted for. Finally, because the volume has changed from 2 to 3, our expansion process will actually have a different starting volume. Because of this, we will also need to calculate an expansion ratio. Once again, the whole process of finding fuel mass, heat added, and temperature rise is going to be exactly the same as that in the spark ignition cycle. Jumping into the code, our calculations for Q23 and temperature are going to remain the same, but this time when we calculate pressure, we keep it constant from 2 to 3. With the temperature and pressure at 3 calculated, we can then rearrange our gas law again and calculate the volume at 3. Now we have all the state variables we need for the working fluid at 3, but we still need to know the work done and the expansion ratio. As discussed before, the change in volume from 0.2 to 0.3 means that work has been done even as heat has been added from combustion. Since this has happened at constant pressure, we can use a simple formula for expansion work, which is just the pressure times the change in volume. So the work during the process from 2 to 3 is just equal to the pressure at 2 times the difference in volume over that process. Next, we need expansion ratio. Since the cylinder has already been moving down from top dead center during the combustion event, our calculations for the expansion process will have a different starting volume. Because of this, the volume ratio during the expansion does not equal the compression ratio. Instead, we must find this new quantity, expansion ratio. It is simply the volume at 3, or the volume where combustion finishes, divided by the volume at 1. With this now known, the isentropic expansion step from 3 to 4 will look very similar to that used during the CV cycle. We're still trying to understand the expansion of the working fluid and the state variables at point 4, but this time the calculations are just done with ER rather than with CR. The equations in code follow the same pattern as was used in the Otto cycle, except replace expansion ratio anywhere you would have used compression ratio. We still need to know the work done over this expansion process, but since work output only relies on temperature change, not volume change, this code stays exactly the same. Finally, we can breeze through the heat rejection process, as again, it's exactly identical to the Otto cycle. With this modification covered, we'll hop real quickly back into Python and take a look at how the diesel cycle works. Alright guys, we're back in Python. Just going to take a quick look at the diesel cycle, the constant pressure cycle. This is going to be very similar to the constant volume cycle, just with a few tweaks. We have upped our compression ratio by reducing our clearance volume. We've changed our fuel parameters, and that's about it for here. Compression stroke is going to remain completely the same. Combustion event is going to change. This is the main part of the constant pressure cycle. So, as before, we find the heat added based on the fuel mass, the mass of fuel air charge, all that. Then we find our temperature rise to 3. This time we're keeping pressure constant. This is the constant pressure cycle. And then we calculate our volume using a rearranged ideal gas law. Work is calculated just as before. Oh, no, sorry. So work normally isn't calculated during the combustion event, but since the volume is changing over the combustion event, we have to calculate it. And then our expansion ratio will be calculated and used instead of compression ratio. So we just throw expansion ratio in here, and the rest of this is very much the same. So let's run it, see what we get. So as expected, the graph looks a little different. So our compression rises, and then we have this flat-topped region. This is our combustion event. So pressure is remaining the same, but things are getting pushed down. Our volume is increasing again at the beginning of the power stroke. So you can also take a look again at all the state variables. P2, P3 is remaining constant, but you will see our temperature is going to increase. Yep, T2, T3, big increase in temperature there during the fuel burn. We did increase our compression ratio up to 18 to 1, so this is pretty typical for a medium or high-speed diesel. 18 to 1 is good. Just comparing with our same displacement from the CV cycle, we lost a little bit of cycle work and IMEP, so power's down. We're going to be testing this at 4,000 RPM, not 9,000, because most diesels don't operate up at 9,000. And our fuel conversion efficiency is 56%. That's about all there is to it. One thing I did add was energy balance. You will see this has changed a little bit from the last energy balance in the CV cycle, because we have to add work to 3. So back in the CV cycle, we only had Q23, that was the combustion event. That's the same here, but now our combustion event has some work. So we needed to add that in just to make sure that, once again, that is very near zero. So that's about all there is to the diesel cycle. This is really just an intermediate step, but I thought I would show it pretty quickly here. Now that we've talked over the real implementation of the diesel cycle, let's move on to the third and final step of the ideal cycle journey. The limited pressure or dual cycle is the final evolution of ideal analysis. It combines aspects of both the Otto cycle and the diesel cycle to give us the most realistic representation of combustion possible in this simple format. So how does it work? The limited pressure or LP cycle begins as the others do with isentropic compression from 1 to 2. From point 2 up to the new point 3 alpha, we see the same constant volume heat addition that was used in the constant volume or Otto cycle. From 3 alpha to 3 bravo, we then see constant pressure heat addition from the diesel or constant pressure cycle. From 3 bravo to point 4, we have isentropic expansion, calculated via the expansion ratio described in the constant pressure cycle, and blowdown from 4 back to 1, just as in the previous cycles. The setup for the limited pressure cycle is very similar to that of the Otto or diesel cycle, depending on which engine you're trying to replicate. The important addition here is the dual cycle fuel allocation. This essentially tells us what fraction of fuel will be burnt in a constant volume fashion, and which fraction will be combusted in a constant pressure fashion. In this case, the constant volume fraction is a user-defined variable, and constant pressure fraction is calculated as the remaining fuel after the constant volume combustion. For a spark ignition engine, we're going to assume that the distribution is half and half. Diving into the workflow, we can skip isentropic compression as it's the same process shown in prior cycles. Constant volume heat addition will look the same as it did in the Otto cycle, but when we determine our mass of fuel, we must multiply it by the CV fraction. This is how it's represented in code. Volume at 3 alpha is equal to volume at 2. Heat added from 2 to 3 alpha is the same equation as we defined previously, but we multiply the whole thing by the CV fraction. For temperature rise, the story is similar. We just include the CV fraction in the heat term when calculating the temperature at 3A. Finally, calculating the new pressure at constant volume is again the ideal gas law. The only difference here is we exchange 0.3 for 0.3 alpha. Now we move on to the constant pressure section of the combustion event. This will work very similarly to the constant pressure heat addition from the diesel cycle, but now we use the CP fraction. Once again, we're running the heat added and temperature rise formulas exactly the same as before, but now with the addition of the constant pressure fraction. Since pressure remains constant throughout this part, P3 beta is equal to P3 alpha. The ideal gas law equation is used to find volume at 3 beta. It's the same as before, just with the temperature and pressure values found at 3 beta instead of just 3. Expansion work is done during the constant pressure heat addition, so once again, work must be calculated. We just change the formula to account for the new points of analysis. Expansion ratio is also the same. We just swap out volume at 3 for volume at 3 bravo. Since our new expansion ratio is based off of V3 bravo already, the formulas and code for isentropic expansion and the work done during this process remain unchanged from the diesel cycle. Finally, the formula and code for the blowdown part of the cycle is the same as it's always been. And that's about all there is to the limited pressure cycle. Let's go back into Python and take a look. Alright, here we've got the limited pressure cycle in Python. We've set things back to how they were for the constant volume cycle. We've got 86 millimeter bore and stroke. We've changed our clearance volume a little bit. This is going to give us about an 11.7 to 1 compression ratio. Values for fuel are changed back to gasoline. Initial conditions are the same. And then we have the important part here. So this is the dual cycle fuel allocation. Right now we have the CV fraction as 5. That means half the mass of the fuel will be combusted as it would be in the CV cycle. And then the other half is going to be combusted in a constant pressure fashion. So code is mostly the same. Compression's the same. Combustion event is pulling code blocks from both of the previous cycles we looked at. So this is just like the Otto cycle. This is just like the diesel cycle. The main change here is that we're putting these CV and CP fractions into the equations where fuel mass would be. So it's basically just dividing the overall mass by the mass for that particular section. So with the diesel cycle here, we're still calculating the work during combustion. We're still calculating an expansion ratio. And these expansion ratios work just fine because we're calculating at 3B. So that's all the same. Blowdown is the same. The energy balance and cycle output have just been modified a little bit to include the third work term here. And then in this case, there's two Qin terms. So all of this is just modified to make sense. Fuel conversion efficiency as well. We now have two Qin terms. All right, let's run it and see what we get. Okay, so pretty much as expected here. We've got the compression as normal. We have a spike for the constant volume combustion, and then a bit of a horizontal leg for the constant pressure combustion. It's just a combination of the last two cycles. So we can play with this a little bit. We can basically say, let's have our constant volume fraction be a really big number. So almost 1. If we do that, that looks a whole lot like the constant volume cycle. If we make this constant volume fraction a really small number, so now our CP fraction is going to be very near 1. It looks like the constant pressure diesel cycle. So you can basically use the limited pressure cycle code and run any of the three cycle types. You just want to nearly zero out either your CV or your CP fraction. One thing we can look at, we can kind of get an idea of combustion efficiency. So with our original half and half, we were looking at 1.07 kilojoules for work and 61% efficiency. When we brought all of the fuel back into the constant volume regime, we actually went up to 1.1 kilojoules and 63% efficiency. And then when we go down to the constant pressure, doing all of the fuel burn, we actually lose a ton of cycle work and efficiency. So it's kind of interesting. Just shows you kind of some different effects of where that fuel's burnt. There's a lot of different reasons for this that are outside the scope of the video, but it's an interesting thing nonetheless. One cool thing we can do with this, let's go back to about 0.5. So this is obviously all data being pulled from our calculations here in the code. What we can do is actually look at what a real pressure versus volume diagram looks like for a real engine. So if I pull this guy over, this is actually your I should say somewhat real PV diagram. So it's not straight lines, it's not nice like that. It's kind of more of a kidney shaped or a liver shaped. So one thing we'll note is if we are all the way to the CV side or all the way to the CP side, neither of those graphs really look like the ones we're interested in. So that one's a little too boxy. This one's going to be a little too narrow. But, you know, if we go back to 0.5, it's going to start to look a little more reasonable. So this looks a little bit more reasonable. We could maybe even have a little more constant pressure fraction. So let's say we are at 0.3 on the constant pressure fraction, or constant volume. So there, I mean, you're starting to look a little more realistic in terms of what that cycle actually looks like. So that's one thing that we can tune in to give us a lot more realism on the limited pressure cycle that we couldn't do with either of the previous cycles. The two-phase style of combustion that we have added with the limited pressure cycle is about the end of ideal cycle analysis as far as the textbook is concerned. From here, though, we can start making some modifications that add realism to the cycle. I'm putting these modifications in an appendix to differentiate them from the work we've done so far. Up to this point, we've been following well-defined thermodynamic laws and processes, Now, we're going to lean more on intuition and numerical modeling to summarize a whole bunch of very complex factors. I said we would come back to mean effective pressure later in the video, and now's the time. This will kind of guide the modifications we want to make to the cycle as we add in realism. But for mean effective pressure specifically, it turns out that there's a number of different types. The one we've talked about so far is just defined as the work of the cycle over the volume displaced. Now, if we take this and find mean effective pressure from in-cylinder data, it's called indicated mean effective pressure. Typically, this is going to come from a high-speed pressure transducer inside a running engine, and you'll get actual measured data. In this case, we're taking the indicated mean effective pressure from our ideal cycle, and specifically it's coming from the power loop, so the compression, combustion, expansion, and blowdown. So when we do an ideal cycle and we do just the power loop, this is gross data, or gross indicated mean effective pressure, GIMEP. So what's this going to look like? Well, GIMEP is basically the graph that we've been looking at the whole time. It's just the PV diagram, just the power loop here. There is more we can add to the cycle, however, to make it more realistic. All right, so we just talked about how this part of the PV diagram we're looking at is the power loop. So we have compression, combustion, expansion, and blowdown. But we're still missing something here. If I throw the more realistic ideal cycle diagram up on screen, you can see that we're missing that whole region at the bottom. That's what's known as the pumping loop, and it's going to try and describe a real intake and exhaust stroke. So that's pretty complex to model, but we're going to approximate it roughly here. So what we're going to do is we're going to add a section here after blowdown called the pumping loop. And we need two primary things for this. The first that we need is an exhaust pressure. So this is going to be 350 kPa, about 1.5 atmospheres above what atmospheric pressure already is. This is going to basically simulate the restriction and back pressure of the exhaust trying to be forced out of the exhaust valve, the port, any manifold, or mufflers, catalytic converters, anything you have in the exhaust system. This is going to collect that restriction. And then we need a pressure of the intake. This I'm putting at 250 kPa below ambient, so we're at negative 150. Again, this is going to represent all the restrictions in the exhaust system. So the cylinder is going to be moving, or the piston is going to be moving down in the cylinder, and it's pulling against all the restrictions, the valves, the ports, the butterfly valve for the throttle, and basically we're getting a vacuum restriction here. So with these two pressures, we're going to take our PV diagram and we're going to add 4 more points. So we have 1, 2, 3 alpha, 3 bravo, and 4. Normally 4 goes back to 1 for blowdown, but now we want 4 to go to 5. And 5 is basically just going to be the cylinder lowering in pressure, partially a blowdown phase here, until it reaches the pressure at the exhaust. From there, P6 is just going to equal P5, and then we're going to have P7 and P8, and both of those are going to be at the intake pressure. So they're going to drop from the exhaust back pressure down to the inlet restriction intake pressure. So we have our pressures. Then we got to throw a bunch of volumes up here to complete the PV diagram. All right, so volume at 5 is bottom dead center. Volume at 6 is top dead center, bottom dead center, or excuse me, top dead center back to bottom dead center. So those will be the volumes. We don't need to know temperatures here, although we could calculate them if we wanted. And both of these, both pushing the exhaust gas out and pulling the intake charge in, is going to take work. So we need to calculate some work terms. Work from 5 to 6 is the pressure at 5 multiplied by the difference in volume. And similarly, work from 7 to 8 is going to be very, very much the same, just now happening at the intake pressure. All right, so that's the pumping loop. Let me change something here. Okay, so all I did now was just change our graph output a little bit, just to make sure our plot still looks pretty. But if we run this, there we have a pumping loop. So this is way more realistic than what we had before. It's going to start to look a little bit more like our our kind of real example of a PV loop. So we have the power loop now and the pumping loop. All right, so before we were just talking about GIMEP, which was the power loop part of the ideal cycle PV diagram, but now we can go ahead and talk about PIMEP, or the pumping indicated mean effective pressure. This is the work done over the pumping loop of the PV diagram divided by volume displaced. It's important to note that this whole term is going to be negative. We are going from a high volume to a low volume, and then from a low volume back to a high volume, but the high to low volume is pushing against a positive pressure, while the low to high volume is actually pulling against a vacuum, so there will be resistance there and work into the system in either case. So now that we know about pumping indicated mean effective pressure, we can talk about the net indicated mean effective pressure, NIMEP. This is going to work just like your taxes. When you get your paycheck, that's your net paycheck. It's your gross pay minus taxes. PIMEP is basically your taxes. So essentially, net indicated is going to be the gross indicated, just the power cycle, minus the work that you have to do to get air in and out of the cylinder, the pumping indicated. In a real engine, this pumping work is not done for free, so adding it into our ideal cycle analysis really beefs up the realism here. Here's one slide just to summarize what we've covered so far. Up till now, we've only been talking about indicated values. Remember, indicated values are those coming from an in-cylinder pressure measurement. So that could be a real measurement from a running engine, or it could be the cylinder pressures generated by our ideal cycle. What we might be more interested in is the performance of an entire engine, or what kind of output we're getting at the crankshaft of a real engine. In this case, we have to make another modification. When mean effective pressure is found from a running engine, and this can be measured on a dynamometer, it's known as brake mean effective pressure. This is something you'll hear commonly thrown around by engine people. It's a great measurement for comparing one engine to another, and it's commonly advertised in the more technical publications. So can we estimate the brake mean effective pressure with any level of accuracy, given all that we have right now? Well, maybe, but what we have to do there is account for the losses of a real running engine. It may or may not be intuitive what those losses are, but this might help. This is a Sankey diagram. It's basically an energy flow diagram for an engine. Here you have fuel combustion, which is the energy that we're worried about putting in, and then it's breaking down what percent goes to vehicle operation, friction, coolant, and exhaust gas. These are pretty standard numbers, but this is also a very basic diagram. They can get a lot more complex. For example, this one's taking the entire fuel demand over the life of a vehicle. The thermal energy used to the cooling and the exhaust is pretty similar. But furthermore, they also break down what's being done with the mechanical energy. Is it road resistance? Is it drivetrain losses, aerodynamic resistance, or just idling without doing any work? So these diagrams can get as complicated as you really like. Here's another one that's saying that our exhaust is 19%, combustion irreversible effects are 20%, heat loss is 15%. These don't all agree with one another, but it's because there's a large variation between different engines. Here's one that I particularly like. This is a BMW 801, so the engine that was used in the Focke-Wulf 190 fighter aircraft during World War II. This diagram's actually out of a really good book called The Secret Horsepower Race by Callum Douglas. I highly recommend it. And then here's another book reference. This is The High-Speed Internal Combustion Engine by Harry Ricardo, a really good engineer in the mid-century of the 1900s, who did a ton of really fundamental combustion engine research. Just reading through his book and pulling out some of the critical factors, we can see on a spark ignition engine with low compression ratio, we've got about 32% useful work with a lot going to the exhaust and some to the coolant. And then with a higher compression ratio compression ignition engine, we've got a lot more useful work out of that, and then a lot less loss to coolant and exhaust gas. So summarizing all this, what do we have to account for? Well, heat loss due to the exhaust. There's a lot of hot, useful gas going right out the exhaust port whenever it goes through the exhaust stroke. Heat energy loss to coolant. There's a lot of energy going from the combustion chamber roof and the cylinder walls straight towards that coolant that keeps the engine running reliably and not melting itself. We've also got the work used for mass transfer, so that's getting the air and fuel mixture in and out of the cylinder. And then we have the work used to overcome friction. So this would be the frictional effects of the piston rings on the cylinder, the engine main bearings on the crankshaft main journals, any other things like that where there's surfaces directly contacting. These are going to be the main things that we have to account for in any analysis. So let's see how it works. Heat energy loss to exhaust is actually pretty easy to take care of. The ideal cycle blowdown process already accounts for most of these thermal effects. The Q equals MC delta T, where T4 and T1 are being used, kind of covers most of the heat loss during this entire process. If we want to track how much heat is actually being lost, we'll add a new variable here, which we'll call exhaust coefficient, E of C, and that'll be Q41 over the total Q in during combustion. All right, so in the code, we're accounting for real engine factors, which means I am going to add a new section in here. And we'll just do this between graphs and outputs. So estimating real effects. And the first one we were talking about is energy lost to the exhaust. So this is the E sub C, the exhaust coefficient that we were talking about. And I can throw this in right here. Like I said, this is already accounted for by the blowdown process, and we're still pretty much accounting from 4 to 1. The calculation hasn't changed, even though we have the pumping loop in there. But basically, we're going to look at the Q out from 4 to 1, and we're just going to divide that by the total Q in during our 2 combustion phases. So this isn't going to change any of our results further down, but this E sub C will actually tell us how much energy is lost. So if we were to, for example, build a Sankey diagram for our engine, this is how we would know the energy lost to exhaust. Next, we got to take a look at heat energy loss to coolant. This one's going to be a little more difficult as it's not a really well-defined percentage, but the ideal cycle ignores the waste heat to coolant, so we need to add something to the calculation. The vast majority of this heat loss to coolant is lost during the power loop, so that GIMEP phase, so we're just going to multiply that by a scale factor. We'll add a new user-defined variable called thermal coefficient, T sub C, and this is going to be somewhere between 0.2 and 0.3, so 20 or 30%. Okay, for energy loss to cooling, we're going to add another real effect estimate. So now we need the T sub C, and this is going to be our heat energy loss to coolant. So in this case, we're just going to say it's about 20%. T sub C is 0.20. That can be changed later on as we dial in the simulation. Moving down the list, next we have to account for the mass transfer work, and we've already got this. This is the pumping loop that we added earlier. As we already discussed, pumping mean effective pressure is the quantity used to track this. In the code basis, this is work from 5 to 6 and work from 7 to 8 divided by the entire volume displaced. So that'll just be the pumping loop on the PV diagram, as we said before. So now we want to account for the work done during mass transfer. This one's easy. We just put the pumping loop in a little bit ago, and we got work 5, 6, work 7, 8. So those are really our work terms for that mass transfer, but we want to be able to track that in our outputs. So in addition to cycle work, we're going to add a new term here, and that is going to be pumping work. Let's get this back. So this is just the work from the pumping loop. Work 5, 6, work 7, 8 are both going to be negative, so this is going to be an overall negative term. So now that we have the pumping work, we can get the pumping indicated mean effective pressure, similar to how we got gross indicated. We're just going to take the work divided by the volume displaced, but instead of cycle work, it's going to be pumping work. So we can do pumping indicated mean effective pressure is this same term. We'll actually just plug this in instead. So now we have the pumping work, and with that, we can actually get our net indicated mean effective pressure. It is just going to be the two of them combined. So again, we're going to add it here. That's because PIMEP is going to be negative. So this is really gross indicated minus pumping work. Finally, we get the work used to overcome friction. This one isn't going to rely on the PV diagram as much. The ideal cycle only accounts for in-cylinder factors, so it's not accounting for the friction of the rest of the engine. The friction of the whole crank train is wrapped up in FMEP, or friction mean effective pressure. This is going to increase with engine size, speed, and the number of cylinders you have. So to estimate this, we're going to add a new user-defined variable. We're going to call it the friction coefficient, and it's going to be somewhere between 3 and 7%, or 0.03 to 0.07. To understand the work needed to overcome friction, we'll take the entire cycle work and multiply it by the frictional coefficient. This can also give us our friction mean effective pressure, as we take that entire friction work term and just divide it by the volume displaced. So to account for friction, we're going to go back up to our real effects and add in our last new user-defined variable. That's going to be the F sub c. We're going to keep it at 0.05 for about 5% of the work going to friction. With this, we can develop our work from friction. We'll actually put it down here after the rest of these variables, because they kind of come after what's happening in the cylinder. And work of friction is just going to be negative cycle work. So we're looking at the whole cycle, our gross indicated mean effective pressure, times the friction coefficient. So now that we have the work, we can also generate the mean effective pressure. And that is going to be friction mean effective pressure, which is just the friction work divided by volume displaced. So, can we estimate brake mean effective pressure? Well, we can certainly give it a shot, and here's my best guess. We're first going to take gross indicated mean effective pressure. This is just the power cycle part of the ideal cycle. We're going to take all that and multiply it by 1 minus the thermal coefficient. This is going to simulate the power cycle losing heat to the coolant. Next, we're going to include the pumping indicated mean effective pressure. Normally, you're thinking about this as subtracting pumping work, but since the PIMEP term is negative in the code, we're just adding here. So far, we have gross work with thermal effects factored in, and then we take away our pumping work. This is essentially going to give us our net indicated mean effective pressure adjusted for thermal effects. Now, we just need to put on the friction term. I think this is about as close as we can get to a brake mean effective pressure estimate using the simple terms that we have here. We could go farther, but it would add a ton more complexity in the simulation. Alright, so we have all the puzzle pieces here to actually estimate our brake mean effective pressure, and here's the code. We went over this before, but again, it's gross indicated, factored with temperature effects. You take the pumping work out, and then you take the friction mean effective pressure out. With all these new terms added, we're going to want to revisit fuel conversion efficiency. This is what the modified formula looks like. On the top line, we basically have the BMEP equation, except instead of MEP terms, it's work terms. So this is basically going to be the work of the cycle, accounted for all the thermal, pumping, and friction factors we already talked about. You take that whole quantity and just divide it by the Q in during the combustion phases. Now we'll take a second look at fuel conversion efficiency, and we'll replace the code here. This is going to be our estimate of real fuel conversion efficiency, and you'll see again similar format to the estimated BMEP term, just looking at work and heat in. Finally, we'll take one more look at power. This is what the new equation is going to be. We're basically just going to use the estimated BMEP value and divide it by volume displaced. This gives us the work accounted for all the factors we've already discussed. Then we're just multiplying by the same RPM and conversion factors, and this time we're adding on a number of cylinders. So we're looking at a whole engine with multiple cylinders rather than just one. Finally, we'll come and modify our power here. So we've got RPM, which we still need. We're going to add in number of cylinders because we're kind of looking at a real engine here. And then the power equation itself needs some modifications. So we will come back, and this is going to follow right with all the modifications we've done to estimated BMAP and estimated fuel conversion efficiency. We're actually just going to take that BMAP estimate, multiply it by the volume displaced, so that kind of converts it back to a work term, and then we have all of our same conversion factors, and now we're multiplying by a number of cylinders. Okay, so those are about all the changes that we wanted to make here. Let me just go down and correct all of our outputs so that everything prints out correctly, and we will run this. Okay, so our PV diagram did not change much, but we've got all these fun outputs here. So we now have cycle work and pumping work. Those are going to lead to gross indicated and pumping indicated mean effective pressure, so we can take that into account now. You can see our net as a result. We've got our friction mean effective pressure, and then when we go to our estimated brake mean, that's also putting some thermal effects into the gross. So that's everything accounted for here. Fuel conversion efficiency is looking a little high. Let me actually we can take, and we'll say that we're going to have 25% of heat going just to cooling. So we'll run this. Starting to look a little more realistic. BMF comes down. Our fuel conversion efficiency comes down a little bit. So these numbers are looking pretty good. There's a lot that we can play with here, but we maybe won't spend too much time on that. I'll just point out that we've got 25% to cooling, 5% to friction, and then we have the E sub C term. That's up here. So E sub C turns out to be 41%. So we estimate about 45%. So close to the estimate, but that's all coming out of the kind of states of the expansion and blowdown process here. So that's relatively close. But anyway, you can play with all these factors. You can play with your engine speed, your number of cylinders, and then even go back up and start playing with your CV fraction, and of course the engine geometry here. So a lot that we can do with this, but we'll leave it there for now. That's about all I have for ideal cycles. Man, I had no idea this was going to turn into an hour and 15-minute ordeal when I started this video. I considered this a relatively simple code, and it wasn't until I began a detailed explanation that I realized what a hole I was in. But if you've made it this far into the deep dive, I can't thank you more for watching. From here, I'd like to use this code to make an application with an actual GUI. That should make it easier to distribute and a little more user-friendly. I'd also like to use the program to do some case studies, or show off how it can be used for benchmarking and design concepting. Beyond that, we'll leave behind ideal cycles and move on to the real fun stuff. Believe it or not, this is just the introductory video. Next, we'll move on to more detailed and time-based analysis, but I'll spare you most of the technical detail in the YouTube video. In the meantime, keep an eye out for more videos in the Combustion Engine Fundamentals series. Thanks again so much for watching. Leave a like or subscribe if you learned something. Check out the other videos on my channel as well. Leave a comment with questions or requests for future topics, and as always, tell me what I got wrong. Have a good one.